M1 International Paper, October 2019, question 4. 10 mark of the first part, so we like that. Particle P of mass Km lies on a fixed rough plane. The plane is inclined to the horizontal acute angle theta, horizontal force of magnitude x, axon P. Line of action force in the vertical plane, which contains the line of greatest slope. That just means it's going sort of straight up the plane. It's not going up to the right as it pushes it sideways up the plane. It's going straight up the plane. So the angle it's pushing at is that theta. And the coefficient of friction between P and the inclined planes is mu. When x equals mg, particle in equilibrium. So we're going to put the rest of the force on the r's here. It says on the point of sliding down the plane, which means the friction's acting up the plane. The x is just about big enough. It's just big enough to hold it up and stop it sliding down the plane. It's nowhere near big enough to make it go up the plane. It's just holding it up. So the friction's acting up the plane. So you imagine if the x wasn't there, it'd be very, very small then, and P would just slide down the plane. But x is a bit bigger, but just big enough to hold it in place with the help of the friction. And we've got to show that mu is equal to that. It tells us that x is equal to mg. If I look at the forces perpendicular to the slope, first of all, I've got the r going up to the left. There's the component of the k for the kmg is acting straight down, so that's got a component down to the right. That angle I've got to turn through is theta, because this one is 90 minus theta. So that component is kmg cos theta. The x has also got a component. I've got to turn it through this angle so that it's to make it perpendicular to the plane. That angle, because this one's a theta, that's a 90 minus theta. So we've got to turn it through 90 minus theta. So I've got to times it by cos 90 minus theta, which I can write as sine theta. Looking at the forces along the slope, parallel at the slope, the friction's going up to the right. The component of this x as well has got a component going up to the right. The component perpendicular was mg sine theta. So the one parallel to the slope is mg cos theta, because imagine this angle here is the same as this one. And then the kmg, I'm going to turn it through this angle, which is 90 minus theta. So I've got to times it by sine theta. So it's in equilibrium. It's on the point of sliding down the plane, so the friction is equal to mu times r. So to get the mu, I do friction divided by the r. So the friction is kmg sine theta minus the mg cos theta all over the r, which is take kmg cos theta plus mg sine theta. I've got to get into this form. So I'll divide all these terms by mg, cancel out the mg's if you like. And then the clue here has got tan theta, so I'll divide the top and bottom by cos theta. So I'll have k times sine theta divided by cos theta. It's k tan theta. This term it would be just 1, because I've got minus 1, because I've got minus cos theta divided by cos theta. Here I've got k times cos theta divided by cos theta is just k, and then I've got plus tan theta at the end. There we go. It says deduce that when k is equal to 1, theta must be greater than 45. Well, the friction is going to be positive. The mu can't be negative either. It just doesn't make any sense. This top line needs to be positive. And if k is equal to 1, then tan theta has got to be bigger than 1. For tan theta to be bigger than 1, the theta must be bigger than 45, because tan 45 is 1. And an angle bigger than that, the tan is greater than 1.